I started my studio in 1999, designing and making furniture, but really coming from a maker's perspective. And the early work was really kind of contemporary interpretations of vernacular design. And I suppose about 5 or 7 years in, I started to really develop my own design language, which became much more free-form, much more sculptural, but the forms were really coming from the material in a way. The process was very much about drawing and then making scale models with the material, so kind of sketch modeling, and then working from there up to presentation models, and predominantly in wood. So that kind of brings me up to sort of today, where we've about 15 people working in the studio. For the most part, are involved in the crafting of the pieces, and the process remains largely the same. So our involvement with CAD or Rhino has been very light touch, really, over the years. It's been a process of me doing a drawing, making a sketch model, capturing that and scaling it up in order to output drawings to make it on a large scale. So the piece that's shown here is in a piece titled Enigma, and it's a shelf. It was made for a client in India, a custom-made piece, or a commissioned piece, and it was 6 meters tall. And that piece was 2014, and it was, I guess, the largest piece we'd made in terms of within a space. And we started to realize that making pieces on that scale, that we were going a bit beyond the kind of what we could feel intuitively in terms of the strength of the wood or how it might perform, and that led to this next piece, which was called Magnus, and the first piece we made in the Magnus series, which is really a kind of large scale. This was a piece we made for an exhibition in the New Art Centre in Roach Court in Salisbury here in England. And this piece is 22 meters end to end. So this came after, say, that tall Enigma shelf. And I might just, you go back a little bit, Miro, just look at the shelf. So the shelf is, wall mounted, well supported. So there's only a few elements where the material is moving very free. So there was no great demands in terms of understanding the piece structurally. We just kind of stretched up from where we had been. Whereas when we went to the piece, the Magnus piece, it was really about creating a sculpture within the space. So kind of as you enter into the space, you had this immersive experience. You were within this sculptural form, and it's actually a desk. So it's kind of, you're sitting at a desk, and the form is spiraling throughout the whole space, fraying apart. There's a skylight above, so the light comes down through the layers, and as the light changes throughout the day, the shadows move from the layering. So in this instance, it was made for exhibition, so you can see there's a plinth underneath it, and it was a temporary installation as opposed to mounted. So this was the first time where we really needed to engage with the kind of technical drawings of the piece in a very serious way, because we started to think about the mounting of the piece, and how fine we could make the connection to the floor, the load that would go into the building from the cables that suspended it. So I'm just going to step back, and I'm going to slightly kind of race through this piece, because it's the first piece is 2014, and it was our first engagement with, and it was really a developmental piece. The next Magnus piece we're currently realising, so and it's for a church in Verona, and we're about to go into a whole phase of realising these very large sculptural pieces. So I'm just going to kind of race through this a little bit, just to give you an overview, and then Miro's going to explain how we're resolving and getting into it in much more depth in the series now as we're working the Verona piece. So just the process starts with just literally hand drawings, sketches like this, then sketch models. So this is maybe 1:10, 1:5, 1:10, very thin layers of wood, so you're getting an understanding of how the material will interpret the form. Magnus idea, completely crazy. A desk that would just spiral and take the whole space, and you'd walk through it, and there's a shelf. So this was the first kind of presentation model. And in this, we have just the foot meeting the floor, light touch, the piece spirals through the space, supported by a few cables. And then when we went to the actual stage of doing the working drawings, we weren't sure, because of the scale of it, 22 meters and 900 millimeters wide at the desk, what kind of loads it was going to send back into the floor, cantilevering it. So we were designing in this metal reinforced bracket. It was quite ugly and over-engineered. And so at that point I started a conversation with Arab engineers. They'd asked me, so this was the first metal bracket that we designed. You can see it in orange, and it's quite massive and quite ugly, and not as slick as was in the first model. So I met with Arabs. They'd asked me to do a talk about the studio and the work, and then I kind of discussed this piece we're making with them. So they started to assist us on the engineering side of it, and it was really quite an interesting process, because their initial engagement was, what we had designed in the model is probably right. They're saying, there's a lot of strength actually in the laminated wood, and if it's what you've done intuitively coming out of all of that work for how many ever years, it's probably right. So you're probably over-engineering it with the huge metal bracket. So let's test the performance of the wood and see if we can design it within the constraints of the original model. So it was really quite an interesting exercise, because just the previous slide is us doing a kind of a test on the flex of a piece of ash laminated 100 millimeters thick. And the team we're working with in Arab said, this should fail at about 270 kgs, I think, based on their standard data on a piece of laminated wood. But so we loaded it and loaded it and loaded it, and we got up to about 880 kgs, and it's there at 880 kgs. And we sent a picture to the team in Arab, and we said, we've run out of weights, we've run out of concrete blocks, and we're going to have to set it up again if we're to try and put more weight on it to get it to break, because they wanted us to get it to fail. And immediately the phone rang and said, stop, you're going to pull down the building. They're looking at what we'd connected to wasn't exactly nearly as strong. So it started to become a really interesting exercise for us in terms of understanding the real performance of the material we're working with. It was down to the selection of the grain of the wood, the quality of the lamination, and for them as well, it was kind of generating data so they could give us much more accurate feedback in terms of performance. So these are some of the analysis they were running, and then some of the connections within on the right-hand corner here. Obviously 22 meters end-to-end for logistical reasons and everything. We couldn't leave it in one piece. So we designed a joint on a radius which is concealed, the wire connections that hung the piece. So this is looking at the connection points, and this is all coming out of the analysis they ran on the piece. The bracket, kind of cantilevering toe bracket, which is concealed within the plinth, which would ordinarily be put into concrete on the floor. We have a lot of slides, so we're going to run through this quite quickly. So this is just material list breakout. This is preparing, selecting the wood, so cut into very thin layers. And the joints in the wood. Yeah, you can run a little bit, I think. So this is the laminating the desk section, which was in a former, and bracket design. And this is forming the actual piece. So on the left-hand side, you can see we've gone from the model, sketch model, to making a full-size model. So using the actual wood, just with strings, seeing how it would perform in practice, because obviously working with wood, you're working with natural material. Each cut of wood, depending on the growing circumstances or depending on the grain orientation, it's going to behave slightly differently. So we needed to do this exercise to map it out and see, if on the full scale it was going to perform in the same way that we'd planned in the model. This is doing the actual gluing. You can see our building isn't long enough. The veneer's going all the way out the door. Forming it, and the layers taken apart. And this is where it goes from the solid into the free form, and then the next slide has the layers part, carving, shaping. So this being the first piece we'd done at a scale, it was really, we were learning a lot and kind of the hard way in many ways. So then this is the completed piece. We did templates that fit into the actual building so we could assemble it. All of these tables and props, so the assembly sequence that there wasn't disproportionate load put on a joint until it was all fully assembled, and assembling it. And this is the makers with the team from Arup, and on the right hand side you've got Peter Flynn from Arup in Dublin saying, when we take the jack out, it's just going to drop 7 millimeters, and he's there with his fingers going, see, I told you it dropped 7 millimeters. And the finished piece. So, having made this in 2014, we had a very positive response to it as a concept. It was basically coming out of 5 years previous work, but really scaling it up and site specific. So from that came some commissions. But so this year we're starting that process of some of the commissioned work that came out of this development project, and we've had to think the whole process through from start to finish again, because in the first piece there's such a learning curve, so many things done the hard way, and this is where Miro started to play a very big role on the first project we're working on since, which is an installation for a 15th century chapel in Verona. So, for instance, did that kind of sketch modelling stage on the full scale is Miro is able to generate much more accurate drawings, which is able to get more accurate feedback from the engineers, and now I'm going to take over the exercise of the slides and leave Miro do some of the talking. I'll just race along. This is the final installation, and this is the start of the Verona project.
Okay, so as we already mentioned, this is the second project we want to talk about today, and it's for the 15th century church in Verona. We have commissioned for 2 pieces, 2 big shelves. You can see on the sketches here. And these are actually quite big because they're like 7.5 meters long and 2 meters wide and 5 meters tall. And we are not designing only the shelves, we are designing also 13 glass oil lamps and service ladder and secondary altar that can be moved. So here you can see some simple visuals we made for the client. Here are some sketches of the oil lamps, which are also quite big. They're about to be like 900 mils to 1200 mils tall. And there's going to be 13 of them, and they're going to be 4 meters above the ground on the shelf. So we're solving a lot of problems about how to clean them and all the maintenance, how to actually set them on fire as well. So here you can see one of our presentation models, which is made 1:10. I think the candles in there are quite cool.
Yeah, so this project presented kind of amplified challenges in a way compared to the first piece we did in Roach Court. Number one, the piece we did in Roach Court was an exhibition. So the intention was to develop the piece and exhibit it in that space for 3 months. The conversation here is completely different. The church is in the same family since it was built in the 15th century. And every time we talk about this installation, they're saying, so it's good for 200 years, or the outlook is completely different. So designing the connection between the pieces and the building, and understanding those loads, understanding how we connect kind of brackets to those ancient walls that have actually grown over the years because the building was increased in height about 150 or 200 years ago. So this kind of refinement of the drawing process has been kind of a major step in understanding the performance of the piece, the loads, as said, to go back into the brackets, and there's even the vessels and location in those, and
the whole project is kind of not easy to coordinate because we need to coordinate the precise position of the anchors in the church wall and also in the floor. And I think you can imagine that if you're drilling in the marble floor, you want to be completely sure where you're drilling. So this is why we actually really need to have the precise 3D models and precise drawings to coordinate with Arup, who take care about the anchors. So Michael Day from Arup was there with us in December on site when we built an 1:1 template at place. And for example here, can you see the mouse? Yeah. Here you can see a sample of the wall. So Michael Day was studying this quite
yeah, in detail.
precisely.
Still did, even though Miro did very accurate drawings, and Miro can explain the type of exercise in drawing and in analysing how the material would perform, etc. We still did a 1:1 model, just one layer thick, so we could see its presence in the building, because obviously even with the best 3D drawings and renderings, they can sometimes, to my mind at least, especially with something that's committed there for so long, distort.
I think it was quite important to really stand in the church and look at the template, and then you could see, okay, this is how it's going to look, more or less. And this is something you can't imagine from the Rhino software. You can have as precise 3D model you can have, but still, like, the feeling is something you have to get at the place.
Yeah. One of so there's so many challenges with this particular project in a way, because even there's one door into the church. It's quite a small doorway. And so here's Miro analysing how to twist it through the doorway. And when it goes in, the long part gets joint and it can never come out. So it's really the definition of permanent installation.
Here you can see a drawing of the lamps we are designing as well. We originally designed something else, but then actually our client encouraged us to go for something bigger, I would say.
It started out as just candles, really, in bronze holders, and because of its proximity to Venice and Murano, the client encouraged us to pursue a glass oil lamp made in Murano. So the process gets one step more interesting in a way for us, because now we're reaching into another material. So Miro doing the same exercise of from the drawing point of view, and then going and working with a studio outside of my kind of comfort zone or understanding or knowledge of material, and still allowing the material and process to find a form, but with the guidelines of what Miro had generated. So this is in Murano, working on the glass vessels prototyping. And the first prototype with the oil lamp lighting. And this is where Miro takes over.
Okay, I would like to introduce you a little bit to the topic how uneasy is it to generate a 3D model of pieces like this, where you have to calculate actually the shape of a wood that is bending. And about the topic of the geometry of bending, you can find entire books. So for example, this is a simple example from a book by Otto Frey, which is showing an example. If you imagine that you would be holding a string with both hands and bending it, the string would always find one final shape. And these schemes are showing like how the string would bend. And it's only one shape in the end. It's called the zero energy state, when you bend something and it's trying to find a state when its own curvature is equally distributed all around the profile. And just to show how big this topic is, here you have 5 models of how you can simulate the complexity of the thing, how you can simulate the model, and this is for just the string. And you can imagine that when we are bending the wood, which is actually like a stripe, that it has some width, it's even more complex because you have another dimension in there. And at first I was trying to analyze the shape mathematically, and this is the result when I had the hypothesis that the surface is actually a part of the conical surface, which I still think it's true, but in the end I decided that it's not really possible to simulate our geometry completely mathematically and describe it with any mathematical equation, because you have much more elements that you have to take into consideration when you're simulating the geometry of a piece like this, which I'm trying to show in this picture. For example, that when the piece is splitting into multiple layers, the layers are actually intersecting with each other, or the piece is intersecting with some external objects. Like you can see, this is just a sketch model, but in reality it's also like this. It can, for example, intersect with the wall of the church. Also, you have to take gravity into account. And last thing is that sometimes we actually take the layers, when we have multiple layers, and change their shape a little bit by force, I would say, to have really the shape that we want, and this completely destroys like the opportunity to describe the shape mathematically, I think. So in the end, I developed a method when I'm using kangaroo and grasshopper to actually simulate the behavior of the piece, and I'm just using kangaroo to work with quad meshes, and I'm using basically just two elements of kangaroo. One is springs and one is planarized for multiple groups of points you can see in this slide. And this is how the final definition can look like. The difficult part about it is not really the kangaroo simulation, but give the kangaroo the proper inputs. So this is showing how it works with the Verona project. The input geometry of the whole thing are just three gears, three red gears you can see in the left top corner, and then this grasshopper definition in the point 1 and 2 from the left. It's developing like a basic mesh, this one. Then I run the kangaroo simulation and I get the final shape of the thing, but it has still no thickness. It has 0 thickness, so then when next part comes, and that's the part where I'm taking the cross sections I want to have everywhere, and I have them here unfolded, and I'm trying to distribute them all along the simulated quad mesh, and then connect them together to generate a final T-spline surface, which you can see here. So this is the method how it's working at the moment, and I'm trying to build the whole grasshopper definition so it works a little bit like, I would call it Lego, because I'm basically just taking blocks, which are, for example, creating a flat part, then another block is creating the part where the piece is splitting into 3 layers or 5 layers, depends on the piece we're working with, and then I have like another part for each of the layers, and then another block for when they come together, and basically I'm having elements for each of the situation you can have all along the profile to generate the input for the grasshopper, for the kangaroo.
I think one of the interesting things about the way Mira's gone about drawing this, and it's beyond my understanding of Rhino, because as I said, my involvement has always been pretty light touch, is that as we're going through the process from the first sketch model to the presentation model to, as you sort of full-size prototype in the church, to then forming the actual piece, at every stage the piece evolves and gets further refined. And we're able to give that feedback to Miro, or Miro's involved in each of those steps, and he's able to update, and it's very agile and very responsive in a way without rebuilding it.
Yeah, I'm actually trying to develop a method that would be really fast for us to generate the geometry, because if you would be modeling something like this just manually, it can take you days, and then if you want to change something, it's not effective. While when you have the grasshopper definition, it goes much faster.
I think the other thing as well is that modelling it in other ways, you model it, you end up with a beautiful drawing, you say, yes, this is the thing we're going to make, and then you go to work with the actual material and it behaves completely differently, whereas Miro's drawings are actually getting really close to how we're finding the material performing in the actual forming.
Yeah, Remy is one of the guys working in the studio. He made a testing model to check if these things are right, and he found out that my mistake is less than 10 centimeters on 7.5 meters. So I think I could say it's working quite accurate.
And it needs to, because you saw the model going through the door. It's quite unforgiving if we were to turn up and it just didn't fit. So.
Maybe the last thing I would say about it is someone could ask me where did I get these 3 red lines, because it's actually quite representing the model already quite good. And this is the input we're using every time, and it's always difficult to get these. Most of the times we're getting them from actually making a sketch model, then taking photos from all the sides, from top side and the other side, putting them in 3D, and then I'm trying to estimate the line in there. Sometimes it gets easier that I just develop a few points and run a spline in between them, and sometimes it's more difficult. We've already worked with 3D scans as well, 3D scans of the presentation models we actually used for generating the digital models after.
Yeah, so this is, I suppose, one aspect and a very important aspect of our challenge to respond to these much larger scale pieces, but obviously the challenges continue all the way through the process in terms of the physical space and the infrastructure and how to actually craft pieces as finely as we do on a domestic scale on this kind of architectural scale. So I think Miro has some pictures a little bit later on of the making. We're right in the middle of making of this piece at present, actually. So here we've moved into a much larger space dedicated to making these large-scale pieces. So here you're seeing myself and Robert, one of the team, with the kind of sketch model in front of us. Some of the drawings. This is the new space. We're still a kind of work in progress, really, but it's a space that we've occupied since making the first piece, and you can't imagine the amount of space it takes up for these large-scale pieces, because when you take the layers apart, it really, it's whatever 7.5 meters by 3 layers is 21 meters. It's a huge. So this is just some of the team working on the material prep. This is forming this actual piece for Verona. So one of the interesting things that we started doing quite a few years ago was forming using vacuum, eliminating the need for formers and clamps. So you're really allowing the material to find the form, and that's the challenge. And of course, it comes right back to what Miro was explaining of how do you generate a drawing of something that's going to be created in such a free way.
I think this picture is a good example of how we are sometimes actually manipulating the shape by force, that it's not just the mathematical surface I was talking about, but that it is really something like free form. So you can see it, for example, here, and here, that the shape is manipulated later. That it's not completely that the wood would be doing what it wants, I would say.
I think this is the final slide, and this is really where we're at right now with the 2 pieces. We've formed the 2 main pieces, and we're entering into the stages now of taking those layers apart and carving and profiling and shaping then obviously all the on-site work, the connection to the church and everything. But the impressive thing is how closely these relate to the kind of modelling that Miro has done, and how it's transformed the process from the first piece we made to this piece, whereby we're going in a very linear line. We're able to give our consultant engineers, Arup, much more accurate drawings. They're able to give us more refined and accurate feedback, and it means we're consistently going forward with the project, as opposed to moments of uncertainty or redoing something because the form is very different from the drawing, or this kind of situation.
Yeah, that's definitely true. And maybe I wanted to say just last thing that the drawings were made in the studio before as well, but mostly 2D drawings from photos. For example, you had the photo plan B of a piece, and Hortons or Michael made the 2D drawings, which is good for most of the pieces. Because the guys making the pieces actually usually just need the top view or the side view together to be able to make pieces like tables or chair, which are not that big, where we don't really need to coordinate something with Arab engineering and other people.
Yeah, typically the work is very much, I'm doing a drawing, a sketch model, and then as Miro explained, our technicians, Michael or Tons, are generating kind of working drawings for that for the team, and then I'm on the floor and just directing a little bit. But they're pieces of a domestic scale, so you're able to look at them, feel them, and direct it. Generally, the dimensional constraints are something like a table needs to be 3 or 4 meters long, or and you have some tolerances. Obviously, projects like this, our tolerances are massively reduced to, I think in this case, we're down to 7 millimeters over the whole project. It's kind of tolerance we built into the bracketing system within the church. So, so this kind of exercise is essential, actually. And the interesting thing about the way Miro's gone about it is how efficient it's becoming, actually, to do this. So each project we do in this series from now on, it becomes a more fluid process to generate. Now, if anyone has any questions.
Hi, really beautiful pieces. I'm just wondering whether you've got, whether you model the actual props and the suspension cables as well in the 3D, or this is something that you do on site, or as you make sort of the sketch models. So how do you know, do you sort of have a 3D grid of where these points of suspension or sort of propping are?
Typically in a site-specific project such as the two we went through, you've got locations where you can potentially have a connection, and you've got locations where you definitely can't. So in the early stages of sketch modelling, we're obviously using these points and working through it very freely. But when we get to the point of the project being a project, the client has commissioned it, and Miro's generating a drawing like this, then we're kind of going across to Europe with a very, how would you say, kind of a very a lot of freedom as to how to optimize the connections, and even maybe optimizing the stability of the piece and changing the form. So because the work is very free, it's not as restricted, I guess, by nature of its function. It's mainly, for instance, this magnet commission for the church in Verona, it's there to create an atmosphere. It's not like a stairs or something with a very fixed performance function, other than somebody needs to be able to get up and light these Murano oil lamps, and they could be 4 meters high as they could be 3.5. So, and the forms are more about the light and texture and the sculptural form than it is, once again, like a stairs or something that's a very fixed function. So when we start into that engineering phase, we're very open to the whole project changing again in a way.
Hi, I've got a question about the sort of suspended vacuum sacks. Obviously beautiful in wood, but have you thought about, I don't know, can you put other materials in with the wood plates, which you obviously make as, I guess, your own plywood, and then you stretch and whatever. But I don't know, could you put in that vacuum bag fiberglass or solid surface with heat, or is there anything that can perhaps go in the bag with it, the vacuum bag, and then you can have things that presumably could go outside, and these beautiful timber plywood forms could be formers rather than...
Yep, you're completely right. A few years ago we did a series in carbon fibre, so using the exact same principle but sandwiching with carbon fibre, same process. We never went beyond the kind of developmental process. They were very interesting. We just got so busy with other things it stopped, like so many development projects. But yeah, the principle works.
Hi there. Just while we're on this slide, how do you deal with a glue line when you come to shape the pieces?
If the lamination is successful, it should be virtually invisible.
One other question while I've got the microphone.
So just to finish that, it's also about the grain selection, because we're reconstructing the tree in a way.
Yeah.
So it's sliced apart and reconstructed as opposed to plywood or the grain orientation. So it's invisible.
Do you do any work scanning the finished or close to finished pieces to make a kind of digital model from what's actually there to compare it to what you've created prior?
On the full scale, we haven't done, no.
No, on the full scale, but already on the models which are like 1:5. We've already worked with 3D scans of a piece that is about to be about 8 meters high, and the model 1:10 is already quite big. So when you have a 3D scan of this piece, you can already consider it quite accurate and quite representing the final piece to work with.
Thank you, guys.
Hi, I am Markus Vikar from Helsinki. I found this very interesting, and also because a couple of years ago we did a similar project at Aalto University, and it was, as in your experiment, it was very hard to predict these shapes on a computer. Now you told that you had used some photogrammetric techniques for getting a close model into the computer, but our pavilion consisted of many discrete elements, but they were made out of thin plywood parts, and we tried all kinds of simulations, even on a supercomputer overnight from the Meteorological Institute, but then in the end we ended up working with physical models, both scale and one-to-one, and I think it would be really interesting to continue on this topic to develop it further.
Both of us could answer that in a way. Personally, I like working with physical models, certainly from the design generation, the feeling the material, how it performs, and studying the form in 3D in hands. And the kind of lead engineer we're working with in Europe is a kind of huge fan of physical models, feeling, touch, just get a feel for how it actually, even on a scale. And then the exercises of prototyping, so you see the actual performance of the material on the full scale. So any kind of analysis you're running, you're qualifying the kind of data that you're running it against, rather than, it's not an area I'm very familiar with. I'm sure there's people in this room much more familiar with it, but the analysis that the various softwares run on, say analysing a material, has obviously got some calculation of how a material performs. With the tests we did where we nearly pulled down our building, we obviously outperformed that data, more than threefold, and I'm sure we could have, if we had actually broken it, probably would have broken at 1.5 tons or something. So I suppose from my point of view, I think there's a lot of merit in getting hands-on, and the combination of hands-on with tools like this can generate some extraordinary results. But one or other in isolation in our time, I think, isn't as relevant. that's fair, but...
Yeah, I suppose you notice as well when you work with these shapes that it's really alive when you're playing with it. For example, when we were building the one-to-one template installation in Verona, we could see that when we built the shape in there, it was really like flowing up and down, and we had to prevent this movement with the rope coming to the ceiling to actually hold the template in place. This is where like the 3 layers or 5 layers places become, I would say, handy maybe, because it's making the shape much more stable. That it's not really that deformed because of gravity.
In the continuation of this spirit, also, I totally welcome the physical models coming from Denmark. Maybe we have a shared Scandinavian appreciation of this technique. May I suggest the use of an old school device, the 3D digitizer arm? We use that for marking up the veneers when they are still flat, just as a ruler, bending it and only capturing the points which is needed. And I know it can be acquired in a larger scale. We have the desktop version, which is almost like a lamp. But I know that Faro are creating a device which is also very reasonable priced, and Geary are using it for capturing the cardboard models also. It's a really, really nice technique in Rhino, and it's also dynamic using the physical models.
Yeah, I suppose this could be a really nice experience, and
yes.
Maybe I would like to try. I've already been trying to take a photo of the sketch models with the grid on the paper behind it, so I could actually see the points accurately on my laptop after where they are in space.
But with the device, you capture the points directly in 3D, so they end up being points in Rhino, the perfect location.
That's why I'm saying it could be really interesting for me.
You need to get one of those.